Merge sort was harder than
Merge sort is a subtle algorithm. In the details, the concept
I think I just
is
got,
straightforward.
I think I just got really lucky the first time I coded it. Because I just coded it. Huh, that works. I moved on, not thinking about it. Spam call.
Okay, let's go ahead and get started. It is 10 after. So today's lab is about implementing skip lists. So skip lists are the data structure that we went over in class yesterday. And part of what you get to experience with this lab is a chance to put together both the skip list itself, which is just a terrific data structure, but implementing it requires implementing a linked list, it requires using array lists, it requires using a stack. It really puts together a lot of ideas that you've been examining so far in the course. So, so here we are. We talked about this yesterday, but I'll review it now. If we want to maintain a sorted list of items, the options we had seen prior to yesterday were keeping a sorted array and a sorted linked list. With a sorted array, the advantage is you can use binary search so you can find things fast and log n time, but inserting takes linear time, very, very slow. A sorted linked list requires using linear search. We can't use binary search, but inserting is pretty fast if we already know where we need to be. What's great about a skip list is that it maintains a sorted sequence, but lookup, insert, and remove are all log n time, and it's log n time for the reasons that we went over in class yesterday. So here's a nice little diagram that arguably improves on what I sketched on in class yesterday that Dr. Yorgi put together that shows the structure of a skip list. Again, we went over it all yesterday, but I'm going to review it with you right now. You have a dummy node at the start of the skip list. Within the list, each node has a random height. So about half the nodes have a height of just 1. A quarter of them will have a height of 2. An eighth of them will have a height of 3. Among 16 nodes, one lucky one has a height of 4. The head node maintains a height which is equal to the maximum height found anywhere in the skip list. So, what's this particular project going to look like? You're going to implement a skip list, basically, is what you're going to be doing. And to that end, I've got a code skeleton for you to look at, and I'm going to walk through it with you right now. Let me make this go away. And at the top level, you have a graphical user interface that looks like this. You can add items, check if it's present, remove an item, or clear the entire skip list. Of course, right now, it's not going to do anything. So if I click add, it just doesn't add. All it has is the dummy node at the start of the list. So to make it work is going to be your job this afternoon. So what is it exactly that you're going to code? The first thing you're going to code is going to be a node for the skip list. And this node in the code skeleton outlines your implementation, but there are going to be some fairly subtle things that you're going to need to do. And there is a language concept here that I haven't really gone over either that I'm going to go over with you now. That language concept is optional. Optional is a data type that's parameterized. That is, you can have an optional of anything. And what optional means is that maybe the data is there and maybe it's not. Using optional is widely considered to be a principled alternative to using nulls to represent the absence of a value. And we make good use of them here in the skip list. And there are a couple of reasons we're using them. First, our skip node needs to represent both a normal skip list node that contains a value and that special dummy node at the very start of the skip list that does not contain a value. And so we make the value optional to reflect the fact that sometimes we care about the value and other times we just don't. The other thing we have is an array list of optional skip nodes. That's an awful lot of data types in one poor variable. So let's talk about what's going on. And to talk about what's going on, I'm going to jump back to the cool Yorgi created diagram over here to think about the relationship between the structure of the skip node and an abstract visual representation of it. So if you look at these things, the head, of course, has no value. That's the optional not there. Something like this node right here does, of course, have a value. It has the value 1, and then it's got a whole bunch of forward links. So the way we're going to represent that whole bunch of forward links is we are going to have an array list containing those links. So an array list contains those links, and within each link, maybe it's pointing to an actual node, or maybe it's pointing absolutely nowhere, right? So if a node is at a given level, represents the final entry in the skip list at that level, it's not pointing to anything. And so we're again using the optional idea to represent that nothingness as opposed to throwing a bunch of nulls around. What does everyone have against nulls? Let me show you something. Here's a title of an article. Null pointer references. What? Stupid medium. Okay. Null pointer references, the billion-dollar mistake. So nulls were invented by the British computer scientist Tony Hoare, who incidentally is the same genius who gave us Quicksort. Yeah, so this guy is a certified giant of computer science. He invented the null pointer in the language ALGOL 60 and has largely regretted it since that time. Nulls have no type associated with them. They lead to all kinds of unpleasant errors that are not readily detected by a compiler. So we are rejecting them and using optionals instead. So having looked at that, let's look back at the code and see how that diagram relates to the structure of this code. We have an array list. So here's the collection of all those forward nodes. Each entry in the array list is optional. That means the thing might be pointing to nothing. And then if it's there, why? It's a skip node. But the skip node, of course, has a parameterized type for its value. So one innocent looking variable, 4 cascading data types, but there's a reason for every single one of them. And I hope that's reasonably clear. Now, within the skip node, what you need to implement are several methods, none of which are long. If you find yourself writing more than 3 or 4 lines of code for any of these methods, you're probably doing it wrong. If you find yourself stuck having an existential crisis about how to implement it, you're probably thinking too hard. None of these should be difficult. I'm going to walk through what each of them entails. In the constructor, you're going to create a new skip node object. You're going to initialize it with the data that's passed in, and you're going to create an empty array list. So we're looking at 2 lines of code here to set it up. Get height returns the height of this node. Now, examining the data representation, what do you all think is a natural way to think about the height of a given node in a skip list, given this data representation? Thoughts? I do recommend returning a value. Yeah. But what's the thing we might return given the data representation? Something that corresponds to how many forward pointers we have. What's that, Morgan? Are you referring to this array list? Okay. So what about that array list might we return? We're certainly not going to return the array list, right? The place of what? Every entry in the array list contains an optional skip node.
Question on the optional. Is that another array?
No, it's just either something or nothing. It's either empty or it's a value. Bingo. That's exactly right. The array list contains one entry for every forward pointer in that skip list node. So to get the height, we just return the number of elements stored in that array list. Yeah, it would be that. For get data, we return the data stored in the node. So you might be wondering, how do you get the data out of an optional, right? In this case, what you're returning is actually an optional. So this is going to be a one-liner. Just sort of like think hard about what the data is. Get next is a little more subtle. It returns a reference to the next node on a given level, or optional.empty if the node is not tall enough to contain something at the given levels. So this takes a little more logic than the others. You're going to need some kind of an if statement to get that working. Add next takes a reference to an optional skip node as a parameter and appends it to your array list. That is, this makes your node one level taller. And then set next takes two parameters, a level and a reference to an optional skip node, and sets the reference at that level to be the given reference. But it ignores it if the node isn't tall enough. So again, you're going to need a little bit of logic here. If it's not tall enough, I don't want you throwing an exception. It should just silently fail. That's the skip node. Once you've got skip nodes, let's see. So you won't be ready to run the unit test quite yet. You're going to need to do some stuff in skip list to get to that point. So skip list is a class that begins with a reference to the first skip node, and that skip node is going to be the dummy one without a value. And it's going to have a variable that maintains a size. And we went ahead and created the constructor for you and several other methods as well. What we really want you to focus on is first this all-important, whoops, I am just jumping around here. This all-important method called locate. If locate doesn't work, the whole thing falls apart. Locate is the key to the skip list. So I'm going to explain carefully what we're looking for you to do for locate. Locate searches the skip list for an item, and what it returns is not a single node, but a stack of nodes. So there is a stack data type built into Java, and it's what we're going to use here. And it's got the methods you'd expect, push and pop and so forth. So level 0 from the skip list is going to be at the top of the stack. S- Yes?
The locate function is down here at the bottom here, near the override. It's override string.
Yes, that's exactly where it is.
Okay, thank you.
Yep.
And this one,
Yep, sounds good. So you give it some value you're looking for. You get back a stack of nodes, one node for every level in your skip list. The node at that level either is the immediate predecessor of the node containing the item. So you're not actually going to get back a node containing the item. This is really important. What you get back is the node before the item. So let's say the item is present. The node you get back is going to have a next pointer that points to the target item. Let's say the item isn't present at that level in the skip list. The node you get back is going to have as its next node something that's bigger than your item. In both cases, the node you get back will have a value that's strictly smaller than your item. Strictly smaller than your item. In other words, what locate gives you is a way to easily do adds and removes. See, if your locate works properly, you've got a reference to the node before the one that you're adding. So it's pretty easy to insert it in place. If your locate works properly, you get a reference to the node before the one you want to remove, which is really helpful for deleting it from the skip list. So locate is just absolutely essential to get right. Let me go over with you our explanation from here. So, as we mentioned, we always start with this dummy or sentinel skip node, which doesn't contain any data. Then, when you implement the locate method, it'll work something like the following. You create a new empty stack of skip nodes. You keep track of your current skip node. You start at front. Front is the dummy node that begins the skip list. Now, you start at the highest level in the skip list. The total height of the skip list should be the height of the front node. So you start there, and you follow links at that level L until following the next link would either take you off the end of the list or lead to a node containing a data item which is greater than or equal to the item you're looking for. If the next node contains the item you're looking for, do not follow the link. What we're looking for are the nodes that precede what we're looking for. So then you push it on the stack, and then you go back up and you search the next level. So if we think about the example skip list provided over here, let's imagine that I'm looking for the number 7. What my locate is going to do is it's going to start here, and it's going to start at the top level, and it's going to look a node ahead, and it's going to see, oh, that's a 1. What's after it? Nothing. Okay, so I'm going to push this node on my stack, and now I'm going to descend one level. So I descend a level, and it's like, well, 7 is greater than 1, so I'm going to keep going. 7 is greater than 4, so I'm going to keep going. 7 is greater than 6, so I'm going to keep going. Oh, there's nothing left here. So this node gets pushed on the stack next. So the bottom of my stack is this thing. The top of the stack right now is this one. And I go down a level. And I look ahead and I see, oh, 9 is bigger than 7. So I'm done. I push this node on the stack. So in other words, this same skip node winds up appearing twice on the stack. And now I'm going to go down a level. So I look ahead. Oh, there's 7. It's equal to it. I don't want to go there. So this same node gets pushed on the stack again as it happens. And then we're done. We have located 7 at that point. And at the very top of the stack is the node that at its lowest level is the best neighbor for that thing that we're looking for. Okay, so that was locate. So now you still actually can't test it very well yet because you can't actually do anything to it. You can't really test the skip list until you can actually add to it. So that's step 3. In order to add a new item to the skip list, we use locate to find where it should go. Next, we decide how tall to make the new node using coin flips. To simulate your coin flip, use math.random. Math.random returns a value between 0 and 1. Go ahead and add a level if the value returned is less than 0.5. So here is how insert skip list node is going to work. And so in the code, insert skip list node is physically above locate. Whoops. Here it is. So this stack of nodes right here is the stack that gets returned by a call to locate. So insert skip list node depends on locate working correctly. So that's where it is in the code. Now, looking back here, how do we do this? We create a new skip node. That's the thing we're going to insert. When you create that new skip node, of course, you want to give it in its constructor the value that it should receive. So what do I mean by that? Anytime you construct a skip node, you give it a data value. The syntax for this, by the way, is going to be, so I'm just going to note this here for your reference. If you use optional.of and then give it some value, like say data, that creates an optional that wraps that value. So that's what you want to use is optional.of. Okay, so having optionally of'd, the next step is, whoops, let me come back here, is you pop the first skip node from the stack. That's the previous node at level 0. You insert your new node right after this level 0 node by doing your basic linked list insertion. You put, you have your new node point at whatever the previous one was pointing at, and then you change prev to point at your new node. So to do that, of course, you're going to be relying upon, if we come over here back to skip node, this set next is going to be what you need. Okay. So you add that reference, and now we decide how tall to make it by doing our coin flips. So as long as a coin flip results in heads, in other words, this is a great place to use a while loop. A while loop is your friend. So as long as that happens, you want to have some variable that tracks your height. So you increment the current level. If your stack is empty, then you add an optional.empty reference to the top of the new node. Let's think about what it means to have a stack that's empty. If we come back up here to our diagram, let's imagine that we are adding 7.5, okay? So we're adding 7.5, we put it between 7 and 8. And now we come up here, and what was on our stack was this 6. So that gets pushed on, and then this gets pushed on again, and so forth. So it seems like if we're not increasing the height of the overall skip list, this shouldn't really happen. Of course, sometimes that's going to happen. And the way we keep track of that is by adding these optional empty references. See, if we're adding something that's higher than the height than the skip list currently is, we know it's pointing to the end. because there isn't any other node that's out there. And then what we're going to do is patch up our front node when we're done. So if the stack's empty, that's all you do. Otherwise, you pop a skip node from the stack and insert the new node after prev on that level. So initially we inserted at level 0, then we're going to insert at level 1 and so forth. And then this is where these optional empties come in. We may need to grow the height of the dummy node at the front of the skip list to match the height of that new node. So as long as the height of front is less than the height of the new node, keep increasing the height of front by adding references to the new node. And once you've created this, then you're ready to implement the add method. And so I've got the add method sketched out for you here. And what add is going to do is call locate, and then it's going to call insert skip list node. And then it's also going to increase our size. It's going to bump up our size by 1. So once you've done locate, and once you've done the insert, add is just like 3 lines of code, which is great. You're just putting together a few ideas at that point. On a related note, you're ready to do the test add and test height unit tests. And we've also got a toString method implemented, and that's going to be visualized in the graphical user interface. So here's a typical string it might display. At the start, we have our dummy node, and this is its lowest level, and this is its highest level, okay? And so at its lowest level, the next node has a value of D. And if you traverse the lowest level, you find that the next node always has the value of its immediate predecessor. And that's good. That's the way we want it, because every node has to be represented at the bottom of the skip list. Note that the final node has this slash. The slash means nothing there. Now let's look at the next level. From the front, we actually have to go 3 nodes ahead until we find something. And that's that node N. From that node N, we skip 2 nodes to get to the node R. From R, we skip 2 nodes to get to U. And from U, we skip to Z, and then Z is a null. And then from the dummy, we go straight to R. R goes to U, and then we're done. And then at the top level, R, we have R, and then it just goes nowhere. And so this is really, really helpful in debugging. You should be able to add nodes through the user interface, and the representation should match what you are looking for. That's step 3. Step 4, you're going to add lookup and remove. That's correct. Once locate works, once the insert works, the rest of this is downhill energy, which is good. So lookup, you call locate, and you check whether the node on top of the return stack points on level 0 to a node containing a data item that's equal to what you're looking for. If so, you return it, otherwise return optional.empty. Next is remove. This calls locate and then removes the node from the list if it's there. And you have to kind of walk upward through your stack to make sure everything's in place. Then just play around with it a bit. I want you to create 3 skip lists each of sizes 8, 16, and 32. And then I want you to copy the string representation of that list into your document. And then I want you to answer these questions. What's its maximum height? How close is it to the log of the list size, log base 2? How many nodes have height above 1 but below the max? And how well dispersed are those tall nodes throughout the list? All you need to submit are skiplist.java and skipnode.java along with that evaluation document. And that's the skip list. Yes, question.
No question. I'm waiting.
Okay. Any other questions? All right, with a hop, skip, and a jump, you are off. Have fun with the skip list.